Now, the derivative is one of the two most fundamental concepts in calculus. The first, the derivative is one, and the other one is the integral. And the derivative is the basis of something called the differential calculus, and you may wonder why it's called the differential calculus instead of the derivative calculus. And that's for historical reasons, because when the calculus was first invented, people thought in terms of something called differentials, which later went out of style, although they've come back more recently. The purpose of the derivative is to measure the rate of change of things. So if you're interested in change and you want to know how things are changing, it's the derivative that you want. Now, one of the things that the derivative does is and this was the original historical reasons for why people were interested in it in the 17th century, is because it also enables you to construct tangent lines to curves. That is not the cause of its being important today, but I'm going to use that idea of the derivative tells you the slope of the tangent line to a curve, because it makes the whole discussion very visual, and you can actually see the derivative. Whereas if you do other kinds of applications, there's not a clear visual picture of it. So, what I'm going to do is I'm going to make a general definition, and then I'm going to give two examples. There are two ways to proceed always in mathematics. You can either give examples first and then from those extract a definition, or you can give a definition first and then give some examples. In this case, I'll do the definition first. And so we begin by drawing a picture, and I'm going to call that function y equals f of x, and I'm interested in knowing the slope of the tangent line at some point x. And I will draw in that tangent line so you can see it. And I want to know what the slope of that thing is. So I'll write m subtangent. And the idea behind all this is that we're going to look at secant lines, and then we'll go from there. So I'm going to move here from x to, I'm going to take some quantity h, and I'm going to move over to x plus h. We'll make that over here. And, by the way, I'm going to call this point P, and that, of course, is the point x, f of x. And over here, I have the point Q, which is what? Well, its x-coordinate is x plus h, and its y-coordinate is f of x plus h. So that's what this point is. And now, in green, I'm going to draw the secant line that connects P and Q. And that secant line has a slope. And what would that slope be? Well, slopes are usually denoted by m. So I'll write m sub P over sub PQ. And what is that? Well, the slope of a line is the difference in the y-coordinates over the difference in the x-coordinates. So what is that? That's f of x plus h minus f of x. That's the difference in the y's. And what is the difference in the x's? I'm not going to write x plus x minus h, because I can do that in my head. And the answer is h. So that's the slope of the secant lines. And now what I'm going to imagine is, I'm going to imagine taking this point Q. Think of this as a wire, the function itself. Think of this as a little bead on that wire, like they have in pool rooms, where you keep score. And I'm going to take this little bead, and I'm going to move it towards P. So the next time I look at it, maybe it'll be here, and now it'll look like that. And the next time I look at it, it'll be here, and it'll look like this. So here is a whole bunch of secants. In fact, if you're so inclined, mathematicians would call that a pencil of secant lines. And hopefully, and I probably should extend them because they go down here. Now, as Q gets closer and closer to P, I hope that I can persuade you that those green lines become more and more like the red line. So that in the limit, they actually become the red line. Let me write that observation down. The limit as Q approaches P of the slopes of PQ, or in other words, looking at the algebra of it, what do I have to do here in order for that Q to move towards P? I have to do what? I have to let this H get small. And those limits then, in fact, give you the slope of the tangent line at P. And this slope, algebraically, is known as the derivative of y equal f of x at the point when x is at x. And that's always denoted by f prime at x, and that is then the derivative of f of x. And so that's what it is.